Hello children, how are you? I hope you are well. In order to succeed, your desire for success should be greater than fear of failure. So, let us start our success from today's class, that is about the calorimetry. What I mean by calorimetry? It is nothing but the measurement of heat. Measurement of heat. In order to understand the principle of calorimetry, at first we have to know what is isolated system, or I can say here insulated system. From the heat point of view, what is isolated system? Isolated system in the sense, it is, suppose this is your thermoflask. In thermoflask, we used to keep hot substance as well as cold substance. Suppose inside this thermoflask, I have taken the hot coffee. So in this case, thermoflask is a isolated system. There is no exchange of heat from the system to surrounding or from the surrounding to the system. In fact, an ideal isolated system difficult, no doubt at all. What difficult? Suppose in this thermoflask, you have placed some hot coffee. After 1 month, you will say that I should check the temperature of the coffee. It may not be safe. Definitely, there will be little change, no doubt at all. You can't get the same temperature after 1 month. You may get the almost same temperature after 1, 2 hours or 4 hours or 10 hours, not after years and years. So, whenever we consider the ideal isolated system, you can say that there should not be any heat exchange. No heat exchange between the system and surrounding. No heat exchange between the system and surroundings. Neither heat is going to the surrounding nor heat is entering into the system. There is no exchange of heat between the system and surrounding. We say that is an isolated system, or I can say it is an insulated system. I said that you think this is an ideal isolated system where there is no transfer of heat between the system and surrounding. Now practically it is difficult, but we accept here this is an isolated system. So in this isolated system, so our topic is calorimetry. It is nothing but the measurement of heat. What is the principle of calorimetry? Principle is that principle of calorimetry. Heat lost by a hot body is equal to heat gained by a cold body. This is the principle of of calorimetry. Now let us see, suppose this is an isolated system. You think that this wall is made in such a manner, however, the inside heat can't go outside and outside heat from the surrounding can enter into the system. Suppose this is an isolated system. In this isolated system, for example, we have taken water. Okay, you think its temperature is 30 degrees Celsius. If I enter one hot body, suppose one hot metal sphere I have taken, its temperature is 40 degrees Celsius. That means I want to say that inside an isolated system, if two bodies of different temperatures are present, what will happen? So definitely when the two bodies are in contact, there will be a transfer of heat from a body of higher temperature to a body of higher temperature. So I said that, for example, the substance is losing 5 joule of heat energy. How much amount of heat energy will be lost by this sphere? Same heat energy will be absorbed by this water, because both water and the sphere, metal sphere, both are inside an isolated system. That means there is no chance of transfer of heat between the system and the surrounding. Or you can say that the system is provided, however, there will be no exchange of heat between the system and surrounding. So I can say that the heat lost by this sphere is equal to heat gained by this water. That is the principle of calorimetry. Heat lost by a hot body is equal to heat gained by a cold body, provided there is no escaping of heat into the surrounding or into the atmosphere. If the condition is there is no exchange of heat, definitely the heat lost by a hot body will be equal to heat gained by a cold body. Now, let us discuss in detail how to measure the heat. So, to measure the heat, we use the principle of calorimetry. At the same time, we need an instrument, we need an isolated system through which we can measure the heat of the substance. So, for that purposes, we need an instrument. So, the instrument which provides the isolated system, that instrument is nothing but the calorimeter. So, how it is? In fact, we'll write a sound off. You can say it is a U-shaped copper vessel which is placed U-shaped copper vessel placed inside a wooden box. This is the gap between the copper vessel and wooden box. That gap can be filled with the insulated substance like coir, wool. Those substances are insulated substance, means it won't allow the inside heat to go outside or outside heat to get inside. So I said this is the copper vessels. It is placed inside a wooden box. So there is a stirrer. The stirrer is also made with same material, means copper. For example, this is generally we use copper. And here there will be gap through which we can allow one thermometer to measure the temperature whenever we need. So this is just roughly I have drawn about the construction of a calorimeter. So this is calorimeter. It is an insulated system. It is an isolated system through which device we can measure the specific heat or specific heat capacity of a substance. So let us see. For example, we have to measure how to measure the specific heat capacity of an aluminium sphere. Listen carefully. How to measure the specific heat capacity of an aluminium sphere. So, suppose this is the calorimeter. Okay, see. How to measure the specific heat capacity of an aluminium sphere. For example, an aluminium sphere is given. We have to measure its specific heat. Then what do we have to do? So, let mass of aluminium sphere is equal to, I wrote like Ma, mass of the aluminium sphere. Now, initial temperature of the aluminium, initial, let it be equal to T1. How we measure? Suppose in a container you take some water. No need to measure the amount of water, you take some water. You supply the heat. At the same time, this aluminium sphere, what we are using, whose specific heat we want to find out, by the help of a cotton thread, you can immerse this aluminium sphere here and you can supply the heat. From time to time, you can check the temperature. For example, after some times, it reaches the temperature T1. That means the temperature of water is T1. At the same time, the temperature of the aluminium sphere is T1. It may be 20, 30, 50, 100, does not matter. But to measure the temperature of this sphere, I use this water because when I supply the heat from the water will transfer to sphere. So you have to wait until reached at the constant temperature. For example, up to 100 degree you can wait because at 100 degree water will start to boil. Again the temperature will not increase. So temperature not increasing means at the time both the temperature of water and sphere will be same because both are in contact. We know that heat flows from a body of higher temperature to a body of lower temperature until reaching at thermal equilibrium. So, suppose temperature of the aluminium initial is equal to T1. Now, in this calorimeter, you take some water. The water, suppose mass of water is equal to mW. And written mass of water is equal to symbolically mW. Now, temperature of this calorimeter is equal to temperature of the water. You can say initial, let it be equal to T2. Listen carefully. In this calorimeter, you take some water. Suppose mass of the water is equal to mW. Now, the calorimeter and water both are in contact. So, I can say temperature of the calorimeter is equal to temperature of the water. let it be equal to T2. Clear? So now when the temperature reaches at T1, take this sphere immediately and insert into this calorimeter. So there should not be time gap because the heat will escape into the surrounding. So you should take care. However, there is no escaping of heat into the surrounding. So immediately transfer that aluminum sphere here with the help of this stirrer. This is the stirrer. This is the thermometer. With the help of the stirrer, you can agitate. You can stir it. As a result, the heat what will be released by the sphere, it will distribute in the water present in this calorimeter uniformly. So one stage will come when you will find that again temperature is not increasing. Record the temperature. Now the temperature of the calorimeter, that is the final temperature, that is also equal to temperature of the water, that is also final temperature, that is also temperature of the aluminium, that is the final temperature of the aluminium is equal to, let it be equal to T3. Listen carefully. T1 is the temperature of the hot sphere aluminium we have taken. When I kept the aluminium, inside that aluminium lost some heat. After losing the heat, I found the temperature of the water is equal to T3. These three are in contact. Sphere, water, this metal, copper metal of this calorimeter, including the stirrer, is in contact. So the final temperature, let it be equal to T3. Here I have taken mass of the water is equal to mW. Similarly, I can write that mass of the calorimeter. For example, mass of the calorimeter is equal to mc. M1 for the, Ma is the mass of the aluminium sphere, mc is the mass of the calorimeter, mw is the mass of the water. So T1 is the temperature of the aluminium initial, T2 is the initial temperature of the calorimeter as well as water, and T3 is the final temperature of that mixture. That means the temperature of the sphere, temperature of the water, temperature of the calorimeter, all three are same temperature T3. So between T1, T2, T3, I can say that T2 less than T3 less than T1. That means the final temperature is less than initial temperature of the sphere, and this T2 will be less than T3. That means T2 is the initial temperature of a calorimeter. That means I want to say that T3 is between T2 and T1. So T1 is the highest one. So T3 is less than T1, but at the same time T3 is, I can say that T3 here less than T1. At the same time T3 greater than T2. So T3 is less than T1, but T3 is greater than T2. That means T3 is in between T2 and T1. So T2 is the least one, T1 is the highest one, T3 is in between T2 and T1. So let us apply the principle of calorimetry, heat lost by a body at higher temperature, or I can say heat lost by the hot body is equal to heat gained by the cold body. So listen carefully. So I am using the principle of calorimetry, that is heat lost by the aluminium sphere is equal to heat gained heat gained by the calorimeter plus water, or I can write that plus heat gained by water. Heat lost by the aluminum sphere. How much heat lost by the aluminum sphere? That heat gained by both calorimeter and water, because inside the calorimeter we have used one copper container. So definitely that copper container will receive the heat. So how much heat lost by the sphere? It will be absorbed by both calorimeter as well as water. So now heat lost by the aluminum sphere. So what is the formula to calculate the heat? Formula to calculate the heat is M is delta T. M is the mass of the substance, S is the specific heat of the substance, delta T is the change in temperature. In the earlier video I explained specific heat capacity and as well as heat capacity also. So this A stands for the specific heat capacity, or simply you can say specific heat. So heat lost by the aluminium, that is the mass of the aluminium, into specific heat of the, let A say is the specific heat of the aluminium, into change in temperature. The initial temperature of the aluminium is T1. Final temperature of the aluminium is T3. So T1 and T3, I said that T1 is greater than T3. So I can say that this is T1 minus T3. It is the heat lost by the aluminium sphere is equal to heat gained by the calorimeter. That means mass of the calorimeter into specific heat of the calorimeter into change in temperature of the calorimeter. So calorimeter initial temperature is T2, final temperature is T3. So I can say that this is T3 minus T2 plus heat gained by the water. That means mass of the water, specific heat of the water into change in temperature. Here also change in temperature is between T2 and T3. That means T3 minus T2. So I wrote heat lost by the aluminium sphere is equal to heat gained by the calorimeter as well as water, because both are there. So now I can say that if I take common T3 minus T2 here, okay, so I have to calculate the specific heat of the aluminium. This is equal to T3 minus T2 into MCSC plus MW SW divided by mass of the aluminium into T1 minus T2. This is the formula we can use to calculate the specific heat capacity of the aluminium. Now, one small example you see. So, children, don't forget to share this video with your friends. At the same time, don't forget to mention like or dislike with your comment, because your comment will inspire us. If anything is lacking, definitely I shall take care of it. So I expect you have to share, comment, like as much as possible. See here. Suppose, for example, one substance is given, one solid is given. Solid given. Suppose mass of solid is equal to 0.5 kg. Its temperature is given. Temperature, that means T1 is given. Suppose it is 100 degrees Celsius. This solid you kept inside the calorimeter. Inside the calorimeter. Okay? And the calorimeter temperature, suppose the temperature of the calorimeter or the temperature of the water inside that, let it be equal to T2, which is equal to 30 degrees Celsius. That means the water which is inside that, inside the calorimeter, suppose its temperature is 30 degrees Celsius. You took the solid and you kept inside that. As a result, the solid lost some heat. That heat transferred to the water and calorimeter. Suppose now this is the initial, this is the final. This is also temperature of the solid. This is equal to, for example, now it is 70 degrees Celsius or 60 degrees Celsius. 60 degrees Celsius. That means you got T1 100 degree, T2 is equal to 30 degree. Suppose this is equal to T3, you think this is T3, it will be easy to apply there. You got this is the 60 degree. Then how to calculate the specific heat of this solid? We can easily use this formula. Mass of the calorimeter, specific heat of the calorimeter. Suppose mass of the calorimeter is equal to 500, or you can say 1 kg. Mass of the water I have taken, suppose 250 ml, or you can say 0.25 kg. So solid is taken 0.5 kg, temperature is 100 degree. Now calorimeter mass is this much, mass of the water I have taken this much. Then how to find the specific heat of this solid? So you can use this formula. Suppose mass of the calorimeter I have taken 1 kg. Specific heat of the calorimeter. Inside the calorimeter I said that we are using the copper. That means I have to take the specific heat capacity of the copper, which is 0.386 into 10 to the power 3 joule per kg per Kelvin. This is the specific heat capacity of copper. Okay. Next one, mass of the water. Suppose I have taken 0.25. So here what I have used? Mass of the calorimeter, specific heat of the calorimeter, change in temperature. I have to take the change in temperature. So change in temperature, here how much I shall take? Now it was 30. Now it became 60. That means 60 minus 30, that is equal to change in temperature. Okay. So change in temperature T3 minus T2. So T3 I have taken here 60. T2 I have taken 30. That means I can mention here 30. Divided by, again we have to take mass of the water. Mass of the water I have taken 0.25 kg into specific heat of water, that is equal to 4.18 into 10 to the power 3 joule per kg per Kelvin. This is the total mass I mentioned here. Divided by mass of the aluminium. Suppose mass of the aluminium, what I have written? Mass of the aluminium is 0.5 kg. 0.5 into change in temperature T1 minus T2. Here T1 is the 100. T2 is the, so this is, sorry, I have written T1 minus T3 here, by mistakenly I have written. So this is T3, T1 minus T3 means initial temperature of the sphere minus final temperature of the sphere. So this is 100 minus 60. So how much will be? That will be the specific heat capacity of the aluminium. So children, I hope that you might have understood how to calculate the specific heat of a solid by the help of a calorimeter along with the principle of calorimetry. So in the next video, definitely we will discuss about the mode of transfer of heat. Until then, bye. Thank you.